Module 6 is dispersal of data, or variation. Depending upon which measure of central tendency you've chosen, is the mean and median. There are measures of dispersal that go with each. Why do you need to know that? If you're using the median, you're using it usually because there's some problems with the data. They're spread to one side or the other, or there are outliers. You want something to tell you how the data is distributed. If we're working with the mean, then the data is relatively symmetric, but you want to know whether it's clustered tightly or spread apart. And what measures that is the standard deviation. So I will use the median first. We will talk about a box plot. I will show how we calculate that. Going back to the data that we had in Module 5, we had 10 items. If you remember, the median was right here. It was 7.5. We calculated that. Put them in order. There are 10 items. It's an even number, so we divide by 2, and it gives us the 5th and 6th items. The median is going to be between those. So the 5th item is 6. The 6th item is 9. You add those together and divide by 2 to get the value right in the middle of them. So 7.5 is the middle of that data. Do you notice that there are 5 items below that, 5 items above it? Now, we're going to make a box plot. How do we do this? Well, we need 5 numbers for the box plot. The numbers are the median for the middle. We need the high and the low, which would be 2 and 28. And then we need our first quartile and third quartile. What is that? Well, the easiest way to think of it is the first quartile, or the 25th percentile, is the median of the lower half. So if you look just at the lower half, you have numbers 2, 4, 4, 5, 6. Where's the middle of that? There are 5 items. 5 plus 1 is 6. 6 divided by 2 is 3. The third item, the second 4 in there, is the first quartile. I'll put a line under that. And then if we look at the top part, the first 16 is the third quartile. Okay, so those are the 5 numbers. And what I will do is I will build a scale that starts out, if I go from 0 to 30, does that all fit into my scale? Okay, just about. Okay, so 10 would be about here, 20 would be about here, 28 would be roughly right here. I just want to build this roughly to scale. 2 would be down here. The middle is 7.5. 4 would be about here, and 16 would be about here. I put the box between the first and third quartile, and I connect a line up to the top and to the bottom. There's my box plot. This was the number 2, 4, 7.5. This is 16, and this is 28. Okay? Now, just for vocabulary purposes, the range of this data is from 2 to 28. So that is 26 units. 28 minus 2 is 26. So my range is 26. An important piece of data is the interquartile range. In other words, how far from the first to third quartile. From 4 to 16, I take 16 minus 4 gives me 12. There are 12 units between that. So my interquartile range, IQR, is 12. Okay? This is what I'm going to use if I want to define whether or not I have any outliers. Okay? The definition of an outlier is that it is more than 1.5 of the interquartile range above the third quarter or below the first quartile. What do I mean by that? the IQR is 12. 1.5 times that is 18. I take 18 and I add it onto 16. And so 16 plus 18 gives me 34. This is my upper fence. Okay? So 28 is not an outlier because it is not above 34. If I took that same value, 18, subtracted it from 4, it would be minus 14. Obviously, 2 is not below minus 14. So in this data, I don't have any outliers. It is skewed to the right. Why? Because it spreads out to the 28. That would be indicated when I looked, if you remember in the last module, the mean was 10.5. The median is 7.5. The mean being bigger than the median. The mean gets spread by any abnormal pieces of data. So the 28 is far enough away that it pulls the mean to the right. It pulls it up. If the mean was smaller than the median, that would indicate that I'd have a real low number pulling me down and that my numbers were fairly tight to the upper side. Okay, so just knowing the differences between the mean and median will tell you if the data goes in one direction or the other, or if it is relatively symmetric. Okay? And so just for general information, when we talk about an outlier, you would take the interquartile range, multiply by 1.5, add that to the third quartile, and subtract it from the first quartile, and that gives you your upper and lower fences. If a number is outside of those fences, it is considered an outlier. As a matter of fact, the technical term, it would be a moderate outlier. Later on, you will see terms used as serious or extreme outliers. An extreme outlier is 3 times the IQR past the third quartile or the first quartile. So in this case, 16 plus 12 times 3 is 36. So 16 plus 36 would give me 52. If I had a piece of data more of 52 or higher, it would be considered an extreme outlier. Okay? So just to review, this picture, if you look at it, you notice the box shows you where the middle half of the data is. The line on the outside of the box shows you where the lower quarter and the top quarter are. Okay, and so this is showing you that the data is clustered, and it's packed to the low side, but it's clustered between, half of your data is between 4 and 16, and a quarter of your data is between 16 and 28, and between 2 and 4. Okay? Now, what I want to do is shift over to, for this same data, what happens, how do we take a standard deviation, how do we do the standard deviation? Okay, let's see if I could get this all into here. All right. Taking that same data, you see down the left-hand side, 2, 4, 4, 5, 6, 9, 15, 16, 16, 28. That's my data from before. The first thing I want to do is take the number and subtract it from the mean. Okay? When you see this in your textbook, you'll see it as x bar minus x sub I. Well, the x sub I is the individual data pieces. That's the 2, 4, 4, 5, etc. So 10.5 minus 2 gives me 8.5. Then 10.5 minus 4 gives me 6.5. I go all the way down. You notice when I get to 15, 10.5 minus 15 is a minus 4.5. Okay, all the way down. Now, to check myself, to make sure I didn't make a mistake if I'm doing this by hand, if you add up the pluses, they add up to be 33, add up the minuses, they also add up to be 33. That is always going to happen. The pluses and the minuses are going to be exactly equal. The next thing you have to do is to square that number. So I take 8.5 and multiply that by itself. That gives me 72.25. Then 6.5 times 6.5 is 42.25, etc. I go all the way down the list. Okay, so you've got 10 numbers. That's the squares of the differences from the mean. Then I add those up. That gives me 596.5. Right? Remember, this is only for 10 items. Could you imagine if we had 1,000 numbers here, how long this would take you to do? This is why you never want to do it. Your calculator will do it for you, or your laptop. You get this for free if you put it into Excel and just ask it what the standard deviation is. This is just to give you an idea of the work involved in it. The next thing we have to do is to divide it. Now, this is where we run into a problem. What are you dividing by? Well, a dirty little secret. This is the first place you will see a fudge factor. Okay. There were 10 items. If I want the standard deviation for the whole population, in other words, if my population of numbers were those 10 numbers, then I would divide by 10 here and get 59.65, then take the square root of that, and that gives me 7.72. If, on the other hand, those 10 numbers were a sample of a larger data set, then I'm not as accurate. I have to build in, I can't say that the data is distributed by that. I've got to allow a little bit more so that I don't overclaim my data. And the adjustment, the fudge factor, is 1 less than how many I have. So instead of dividing by 10, I would divide by 9. That gives me 66.28. The square root of that is 8.14. So my standard deviation, if I'm working with a population of numbers, of these 10 numbers, is 7.72. If I'm working with this as a sample, then that is 8.14. Now, how are you going to distinguish between this? In the textbooks, they give it to you as, they either don't talk about it or they give it to you as two separate formulas. It's simple enough. The context in which you're working is going to tell you. In a math book, you've got to look at what are they talking about. Is this my whole population or is this a sample? Most of the time, you're going to be working with samples. And so you're going to work with the n-1 that you divide by. Okay? But this is how we calculate it. Now, if you go back to the original data and look at the data, what was this telling me? My mean was 10.5. Okay? And if I went one standard deviation above and below that, so 10.5 minus 7.72, or say roughly 8. 10.5 minus 8 gave me 2.5, and then 10.5 plus 8 gave me 18.5. You notice that most of the data is within that. As a matter of fact, later on, when we get to normally distributed data, you will find that about 95% of your data is within 2 standard deviations in either direction. This is a measure of how spread that data is. Okay? You would not expect anything to be outside of 3 standard deviations, very little outside of 2 standard deviations. In this case, 10.5 plus 16 would give me 26.5. I would not expect anything much bigger than 26.5, and I've got 28. On the lower side, 10.5 minus 16 would be a minus 5.5. There's nothing down there, so it's showing me that I'm spread a little bit to the top side. Okay? And so with the mean, you have to give it the standard deviation. So in this case, if you're using the mean, you'd say the mean is 10.5, standard deviation is 8.14. If you're working with a sample, that tells you that the data is fairly spread apart. Why? Because 8.14 is fairly big compared to where the mean is. And if you're not using negative numbers, that's telling you they're going to be bunched and they're going to spread to the upper side. Especially if you look at the mean is 10.5, the median is 7.5. Just to reiterate that point, it's an extremely important point. When the mean is bigger than the median, that means you're skewed to the higher side. If the mean is smaller than the median, you're skewed to the lower side, or skewed to the right, skewed to the left, as they say. The skewness is always in the direction of the mean. And skewness is the tail on the thing. You've got the big bunch in the distribution, and where the tail runs is the skewness. It's not where the data is gathered. It's where the data runs out. It is not heavy there. That's where you're going to have a few isolated items. Okay? Thank you.